Hello everyone, welcome to the lab explanation video for the Introduction to TensorFlow lab as part of the How to Build and Train Your AI Model program sponsored by my nonprofit InspiredQ.org. The lab we're going to be working with today is adopted from the MIT Introduction to Deep Learning course. This lab is licensed under the MIT license, making it free to use and available to the public. I also edited this lab. To access this lab and go through it yourself, you can go to the InspiredK.org website and click the AI Program Labs button. That will take you to the InspiredK.org GitHub, where you can navigate to the MIT Intro to Deep Learning repository, and then the inner folder of Lab 1 inside of the repository. Then you click the Lab 1.1 Introduction to TensorFlow.ipynb file, and from there, you will be able to click the Run in Google Colab link at the top of the file in order to go through this lab on your own computer. Google Colab is a service offered by Google to provide free access GPUs to anyone with a Google account, making it extremely simple to run any of these labs on your very own computer. So today we're going to be working with the AI Python library called TensorFlow. And first, we're going to install all of the libraries that we're going to be working with today, including TensorFlow, MIT Introduction to Deep Learning's custom package, NumPy, and a library called matplotlib that adds functionalities for different plottings of graphs. These packages are going to take about 2 minutes to install, and while they're installing, I would like to talk about the MIT Introduction to Deep Learning package. It was built by the instructors of the course, and it includes many different dependencies that are used in all of the labs through the course, including NumPy for different NumPy arrays, the datasets library that contains many different datasets we will be using in the future, as well as others. Additionally, it sets up the lab and the behind-the-scenes workings of the labs for access to be quickly done in the labs. So for example, in Lab 1, the introduction to TensorFlow and the music generation with RNNs, we have many different functions. More specifically for the lab we're going through today, the introduction to TensorFlow, we have several different functions that are checking the different shapes of the multi-dimensional arrays we're going to be creating, as well as ensuring that we are writing completely correct code that matches everything they expect it to be, so that way we can go through the lab with an accurate learning experience. So while it is continuing to download, the TensorFlow library is called TensorFlow because it handles the flow or mathematical operations of data types called tensors, which are really just a fancy name for multi-dimensional arrays. They can be represented with 1, 2, 3, or many more dimensions, and they are extremely useful in artificial intelligence when you want to represent your data at a high dimensional level. So the term shape describing a tensor represents the number of dimensions it has, as well as the size of each dimension, meaning how many items are inside of each dimension. Additionally, the rank of a tensor provides how many dimensions the tensor has. So for example, if a tensor it has 3 dimensions, then its rank is equivalent to 3. So now that all the packages have downloaded, let's start with running the TensorFlow code. So first, let's start by creating 0-dimensional tensors, which are called scalar values, meaning that they have no dimensionality and they are simply stored as singular values. We can do this using the tf constant keyword. So for example, let's first define a tensor called sport that contains the string tennis. We do this by having tf.constant, open parentheses, tennis, comma, tf.string, close parentheses. The tf.string in this definition signifies that the constant we are creating is of the type string. Now, for another example, let's define the tensor called number that contains 1.414, etc., of the type tf.float64. We use similar syntax as before and have tf.constant, open parentheses, the number, comma, tf.float64, close parentheses. If we print the rank of both of these tensors, we can see that both of them are 0D tensors, and their rank is 0 because they are scalar values and they only contain one item. So the first one is tennis, and the second one is a floating point value. Tensors can also have one dimension, and that makes them a vector. So for example, these one-dimensional tensors are defined as normal Python lists, but instead using the tf.constant format. So if we want to define several sports, we can use the tf.constant syntax with a list of tennis and basketball for the type tf.string, as each of the items in our list is a string. Additionally, we can create a tensor of numbers that contains the numbers 3.14, etc., 1.41, etc., and 2.71, etc. Because all of these are floating point numbers, we can define them with the type tf.float64. If we print the rank and shape of these tensors, we can see that they are both one-dimensional, as they are defined as lists, which make them have one dimension. And the first tensor has a shape of 2, as it contains 2 items, and the second tensor, numbers, has a shape of 3, as it contains 3 items. So far we've looked at 0 and 1-dimensional tensors, so now let's get into higher dimensional tensors, including 2 and up. These 2-dimensional and up tensors are called matrices, and in future labs and lectures, we will be looking at how these matrices can be used to store all of the data that we will train our AI models on. So first, let's start by creating a 2-dimensional tensor called matrix. This tensor will have a shape of 2 by 4, as it will have 2 rows and 4 columns. The first row will contain the entries 1, 2, 3, and 4, and the second row will contain the entries 5, 6, 7, and 8. So if we use the assert keyword, a method in Python to check if a certain Boolean method is true, we can check if this matrix is of the type tensor, and if its rank, or number of dimensions, is 2. When we print this code, we see that there is nothing outputted, but this is actually good, as the assert keyword will only output something if there is something wrong. This means that our matrix is indeed a tensor with 2 dimensions. If we would like to define a 4-dimensional tensor, then we can quickly use the tf.0 syntax and then input our shape. So if we want to create a tensor of zeros that has 10 images, a shape of 256 by 256 for each image, and each pixel in the image having a R, G, and B value, then we can have the shape 10 by 256 by 256 by 3, where we have 10 images with shape 256 height and 256 width, with each pixel in the image having a R, G, and B value, which is why the last dimension is 3. If we use the assert keyword to check if this matrix of images is a tensor, has a rank or dimensionality of 4, and has a shape of 10 by 256 by 256 by 3, then we can see that nothing is outputted, meaning we correctly created a tensor of zeros that has 10 images, 256 by 256, with a R, G, and B value for each pixel. Now, in theory, this tensor would actually have many different values for each pixel in each image. However, in this case, since we use the tf.zeros method, all of the values are 0. So, as we saw, we created a 2 and 4-dimensional tensor. We show how the .rank and .shape methods are extremely useful when we want to inspect these tensors. So now we can use these shapes to our advantage in order to index and slice these tensors to get certain parts of them. So if we want to get the second row in our matrix 2 by 2 containing a shape of 2 by 4, we can use the matrix open square brackets 1 close square brackets in order to get that second row containing the items 5, 6, 7, and 8 as its own separate tensor. Additionally, we can get the second column at index 1 by using the matrix open square bracket colon comma comma space 1 close square bracket in order to get that second column containing the entries 2 and 6 at index 1. Additionally, to get a specific value from our matrix, we can use the matrix open square brackets 0 comma space 1 close square brackets in order to get the value in the first row, second column. So in the first row, we have the items 1, 2, 3, and 4, and I did that index 0 in our overall matrix. And then the second column is at index 1. So since our first item is at index 0, our second item is at index 1, the item 2 is selected. So when we print all of the values extracted from these row, column, and scalar value executions, we can see that the row at index 1, it has the entries 5, 6, 7, and 8. The column at index 1 has the entries 2 and 6. And our scalar value at the first row, index 0, and second column, index 1, is 2, because in the first row we have the entries 1, 2, 3, and 4, and in the second column in that row, we have the entry 2. Next, I'd like to show how we can do different computations on these tensors, including addition, subtraction, and much more. So first, let's start with a visualization where we want to add two different tensors together to create a final output. Let's say we have the tensors A and B. We want to get an output of C adding these tensors. So first, let's define our A and B. So A is going to be a zero-dimensional tensor with the item 15, and our second tensor, B, is going to be another zero-dimensional tensor with the item 61. To add these together, we can use two different methods, the tf.add or the plus operator. The plus operator will work as TensorFlow automatically overrides the built-in plus operation, so that way we can use them on tensor values. If we print both of these, we get an output tensor of 76, because 15 plus 61 is 76, and these tensors adding together are just like normal addition because they're both zero-dimensional. Now let's look at a more complex example. We still have A and B as our input tensors. However, now we're going to first add A and B to get an output of C, and then subtract 1 from B to get D, and then we multiply C and D to get a final output of E. When we define this, we can first take an input of A and B to a given function, get an output of C by using tf.add on A and B, get our output of D by subtracting B and 1 with tf.subtract, and then multiplying both C and D using the tf.multiply method for C and D to get our final output of E, which is then returned. If we use some example values of 1.5 and 2.5 for A and B respectively, we can call this function on these two tensors, and when we run this code, we can see that the tensor 6 is outputted because C, where A and B are added, is 1.5 plus 2.5, which is 4. D is B minus 1, which is 2.5 minus 1, equal to 1.5. And then E is C times D, which is 4 times 1.5, giving us our output of 6, which we can see. So in summary, we covered how to create tensors of different dimensions, as well as how we can perform computations on these tensors. Now, I'd like to show how we can scale up these mathematical operations on tensors in order to create neural networks, which are the method in deep learning that are used in order to create AI models that solve problems. So, at the core of neural networks are simple mathematical operations. So first, let's define these mathematical operations. First, we have an input of x, and we have two different variables, the weights as signified by capital W and biases, which are signified by lowercase b. The weights are the goal of the neural network to optimize in order to have specific mathematical operations that lead to the input being mapped to the best possible output for a given problem. So to do this, we matrix multiply the inputs and weights, and then add the biases, and then put that output of that mathematical operation through a function called sigma to give us our output. So let's define this using TensorFlow. We can do this by using a method in Python called class, which allows us to create a general object with different methods that can be used. So that way, we can create a reusable object called our dense layer. This layer is called dense as all of the neurons and all of the mathematical operations are connected to each other. So first, let's define a variable called n output nodes, which will be the shape of the output from our layer. So if we set this given output nodes to 3, then there will be 3 items in our output. If we set it to 5, there will be 5 numbers in our output. Next, let's define a build function that will allow us to take a given input shape for an input to our model and define a starting weights and biases. We can do this using the .addWeight method, which is built into our class because we are basing it on the built-in TensorFlow default layer. And then for the weights, we can identify them as weights using the name parameter and the biases similarly with the bias parameter. Then we can define their shape using our input shape and the number of output nodes that we have. I would like to note here that the initialization of these weights and biases is completely random, which is why machine learning and deep learning neural networks have to be trained in order to optimize them for a certain problem. Next, let's define the call function, which will use these weights and biases in combination with a input x in order to return an output. So similar to our diagram, we're going to matrix multiply the inputs and the weights using tf.matmul and then add the biases. So as we can see from our diagram, we matrix multiply the inputs and weights and then add the biases to get a value called z. Then we use a sigma function in order to achieve our final output of y. And in this case, we are going to use tf.sigmoid. This sigma function is called the activation function, and it is usually a nonlinear function as we want to add some variety to our neural network. So besides sigmoid, there are many other types, but sigmoid is one of the most commonly used as it creates an even distribution of values. So now let's set a random seed to 1 for our model so that way we can have reproducible results and verify it with a test built into the MIT deep learning package. And let's define our dense layer with a number of output nodes of 3, meaning that the output of our model is going to have 3 items in its output. Now we can use the .build method from our layer to define it with a shape of 1 by 2, and then we can create a example input with shape 1 by 2 containing the items 1 and 2. Then we can use our layers.call function on this output to get a y, and we can print it and use the MIT deep learning tests so that way we can see if our model is working correctly. It will take a few seconds to load, and we can see that our test is correctly working as we get a pass with the value true. Additionally, our output has 3 floating point numbers as we defined with our number of output nodes and the shape 1 by 2 as that is the input shape that we defined, and the input shape is equivalent to the output shape. Now, whenever we want to create a neural network, we do not have to define all of this by ourselves, as outside of this it can get much more complicated. TensorFlow has defined a many different number of layers that we commonly use in neural networks. For example, our dense layer that we created is already defined. Additionally, we can use a API inside of TensorFlow called Sequential that allows us to chain these layers together as easily as Lego bricks. So first, let's import our relevant packages of Sequential and the dense layer built into TensorFlow, and let's define a number of output nodes equivalent to 3. Next, let's use the Sequential in order to create an empty model called model. Next, we can use our dense layer in order to define it with the number of output nodes of 3, as well as the activation function sigmoid, creating an equivalent layer to what we previously made. Now we can add this dense layer to our model, and this has created a simple model with a single dense layer. Now let's use an x input with the same 1 and 2, as well as a shape of 1 by 2, and let's feed it into our model. When we print this output, we can see that we achieve a similar output as before. However, it is not completely identical as I previously mentioned, all parameters are randomly initialized. So for example, if we run this again, we will get the same value as our model is defined in the same way, but it is not defined with the same randomization as previously in our customly defined layer. So now that we have this ability to chain different layers together and create models with the Sequential API, let's try creating our own custom models. So we can do this by using the model class built into TensorFlow and then modifying it slightly by using a method called subclassing. This allows us to create our own custom class, but also base it on a previous class. So for example, the model class built into TensorFlow. So let's create a model called subclass model that has a single dense layer, and we define it the same way as before with our input number of output nodes and an activation function of sigmoid. Additionally, let's define a call function that returns an outputs for a given inputs that we have to our dense layer. So as before, let's define our model with a number of output nodes of 3, and let's have the same input of shape 1 by 2 with the entries 1 and 2. Now let's call our model on our input, and as we can see, we get a shape 1 by 3 output that is different than before due to the random initialization of parameters, but it does look correct according to our model definition. The important thing about subclassing and defining our own custom models is that we can now add our own custom behavior. So for example, let's say that under a certain condition, we want our model to output the inputs completely unmodified if a certain parameter is set to true, or still go through the process of inputting our inputs to the model to get outputs if that parameter is false. We can create a model called identity model, subclassed from the built-in model from TensorFlow. We can define it as before with a dense layer with our input number of output nodes and the activation function of sigmoid. Now what changed is the call function, where we introduce a new parameter called isIdentity and set it to false by default. So if the isIdentity parameter is set to true, then we return our inputs as is, but if it is remained as false, we run our inputs through the dense layer and return the outputs of the dense layer instead. So if we have our 3 output nodes like before and build our model, we can use the same input as before of shape 1 by 2, and we can try 2 different ways of calling our model, with isIdentity set to false and isIdentity set to true. If we run both of these activations, we can see that the first one with isIdentity set to false runs our inputs through the dense layer to get some complex looking outputs, whereas the identity parameter set to true calling outputs are inputs as is with shape 1 by 2 and the entries 1 and 2. So in summary, we covered how to define layers using TensorFlow mathematical operations, how to create our own models using the built-in layers in TensorFlow, how to create custom models using the built-in models in TensorFlow as well as the built-in layers, and adding custom functionalities to the custom models that we define based on TensorFlow. Now, I would like to introduce a method called automatic differentiation, which allows us to truly train models in TensorFlow by going backwards through our training, through our mathematical operations, in order to see how inaccurate our predictions were originally and how we can change them to make them better. So first, I'd like to introduce the method called gradient tape, which is sort of like a tape recorder that first records all of the mathematical operations we do inside of it, and then using the dot gradient method, plays them all backwards by computing the derivative of all of the mathematical operations to achieve a value called the gradient, which we can use to optimize our model for a given task. So as an example, let's create a variable called x that we'll set to the value of 3. Next, let's use our dot gradient tape method to perform the squaring operation on this variable of 3 to output y. Then let's get the gradient by using the tape.gradient method on this output from the tape with respect to our original variable. And then let's check if this gradient is equal to 6, which it should be according to how the derivative of x squared is. When we run this code, we see that nothing is outputted, meaning our assertion was correct, that indeed the gradient of our squaring function for the value 3 is 6. So now let's look at a more complex example, which we use more commonly in machine learning in order to optimize our model for given tasks and take step towards higher accuracy. So first, let's define a random variable that is 0-dimensional, meaning it only has one value, and then let's have that value of x outputted to see what we originally started at. Then let's create a target value at 4 that we want our x value to reach, and set a rate called the learning rate, which is the rate that we are going to change our initial x variable until it reaches the target value. Next, let's set a number of iterations that we're going to loop through to change our x value as it gets closer to the target, and let's create a list called history that will show us all of the initial x values as they get closer to our target value in order for graphing purposes. So for each iteration we have of 500, we're going to create a gradient tape and compute a value called the loss for our initial x and our target x. This is done by taking our x value minus the target value and squaring that result. And then with the gradient tape recording that loss value, we can now take the gradient of the loss with respect to the original initial x, and we can use the learning rate times the gradient to change our x in a slight way to take it towards our target value. Now we can change our initial x value to match that new x value that is slightly closer to the target value, and we can append this new x value to show the trend of our x value as it progresses towards our target value. Finally, once all the 500 iterations are done, we can plot our final x as well as all of the changes in the initial value. So we can see that we start with the value -1.1 approximately, and as we go through our iterations of the gradient tape, we get closer to a near 4 value. With more iterations, we get closer and closer to 4, but similar to how exponential functions never reach 0, our function will never actually reach 4, as we can only take smaller and smaller steps towards x, but we cannot take infinitely small steps, which means we will never reach an exact 4 value. So this process of taking an initial value and moving it towards a target value is called stochastic gradient descent. And it is extremely common in machine learning today, as it is an extremely efficient way to train our machine learning models to take our loss towards a value of 0, meaning the accuracy of our model will be higher for a given task we want to complete. So in conclusion, we started by examining what TensorFlow is by defining many different tensors of different dimensions, including 0, 1, 2, and 4 dimensions. Additionally, we looked at how we can slice these tensors with different operations. Then we looked at how we can perform computations for our tensors, including addition as well as much more complex ones. And then we looked at how to define neural networks in TensorFlow using the mathematical operations by defining our own custom layer, defining a model with built-in layers into TensorFlow, then creating a custom model using the built-in models and layers in TensorFlow, as well as adding custom behavior to our custom model. Finally, we looked at a method called automatic differentiation, which can be used in TensorFlow to optimize large neural networks based on data and a value called the loss in order to increase their accuracy and decrease their loss value for a given problem and allow our neural networks to solve large-scale problems. Thank you for joining me today on this lab explanation video, and I highly encourage you to go through the lab yourself so you can understand TensorFlow at a deeper level, as it will be extremely critical later when we want to build neural networks such as recurrent neural networks or convolutional neural networks. So again, to remind you how to reach the lab, you go to the inspiredk.org website, click the AI Program Labs button, navigate to the MIT Introduction to Deep Learning repository and the Lab 1 folder inside of it. And finally, click the Lab 1.1 Introduction to TensorFlow lab and click the Run in Google Colab link to go through it yourself. So again, thank you. And again, I really encourage you to go through the lab. So I will see you in the next lecture and the next lab explanation video. Thank you.